to join Our Ladies Chicago and Our Ladies East Lansing meeting. Tonight's speaker is Doris. Uh, do you want me to introduce you, or do you want to introduce yourself?
I guess I can just introduce myself. That's fine.
All right. All right. I'll
Yeah.
let you take it away.
Hi everyone. My name is Dorris Scott, and I am one of the co-founders of MyR, which is a minorities in our user group. The other co-founder is Danielle Small Perkins, but my day job is working as a geographic information systems librarian, so GIS librarian, and social science data curator at Washington University in St. Louis. Thank you for coming. And I'm going to give a presentation that I've on a topic that I'm very familiar with because it's part of my job, and also it's just something I studied, and that is handling data with dplyr and tmap. Next slide, please. And first of all, I just want to acknowledge that this was a 3-person effort. Actually, this was presented as one of the tutorials at last year's user conference. So Sebastian and Jacob we worked together to create these materials. So if you haven't followed them on Twitter, I would highly recommend you give them a follow. And if you want to see the original material of this course, it is on GitHub. And I might have accidentally not, no. That's the right link. I don't know, actually. Could you just someone put the link in the chat, because I'm a little concerned that I didn't, I feel like it's the right one, but I also don't want to yeah. And so sometimes with these slides, they might not fit your screen. So you can either do Alt plus F or Option plus F to have it adjust to your screen size. Okay, next slide. So I'm going to give an overview of the workshop. We're gonna this was originally a 3-hour workshop, and it's being condensed into 2 hours. So I'm not going to be able to go through everything that Jacob and Sebastian and I went through during USAR, but you'll get a nice taste of how to do mapping in R. And I just also want to caveat, this is not an exhaustive list or methods on how to do mapping in R. Actually, doing geospatial things in anything, whether it's R or Python or either like a GIS software, in 2 hours, you can only just have people, just get their foot wet in the water. But hopefully this will help you move forward in your journey on how to map. So first, we're going to go over the basis of cartography. Then after that, we're going to talk about reading and projecting data. That's extremely important. And that's one of the things that a lot of people who are new in mapping tend to forget. And then it ends up that they have a lot of problems. So I want to spend a good amount of time on that. And then the fun stuff, well, everything's fun to be honest, but drawing maps in R would be our next section. And then the cool thing about using tmap is that you can manipulate the vector data with dplyr. So I'll talk about that. And then finally, I'll give you kind of some more bits on okay, where do I go from here? I'll try to assist you in your journey in learning how to do this. Next slide. So there's going to be 3 exercises to complete. And after the second exercise, there's going to be a 5-minute stretch break. So just, so we'll just tack on 5 minutes to that exercise. So it'll be 20 minutes for the second exercise, actually. And so we're going to assign people up into breakout rooms. And since there are a number of volunteers, it's just going to be 1 volunteer in the breakout room. And since each breakout room is going to be randomly assigned, you'll have a different volunteer each time. Next slide. Okay, let's get into it. So it's very, very important to understand, to have some foundation in cartography before you even start mapping, because yeah, the Earth is not flat like the maps that you create in RStudio. And there are some things that you need to understand that goes in the process of dealing with geospatial data. Next slide. So what is a map? So a map is essentially, you're getting like your globe, like you're getting a 3D, it's not even a sphere. It's that the Earth is actually a spheroid, so kind of an imperfect sphere. So you're getting that and you're splattering it on like a 2-dimensional plane. So, you know, you can have some 3D data and do a 3D globe, or you can have a map, you know, a flat map showing the same range of values that the 3D globe shows. And yeah, there is no flat Earth, okay? There just isn't. Could you press the Alt F or Option F to have it fit to your screen? I don't know what's going on there. Oh, okay. Okay, yeah, could you just do it again? I'm sorry, I don't know what's going on with that.
Sorry, it's not going back.
Could you refresh it?
Yeah.
I don't know. Okay, there we go. I don't understand. Okay, next. Whoa.
Oh, sorry.
No problem.
What just happened? There we go.
Okay, so like I said in the previous slide, that you are essentially getting a 3D surface and projecting it on a 2D plane, but it's not all the same projection. I'm going to go over this really quick because, you know, projections is actually kind of a, there's just so many projections, but these are 3 of them that you'll encounter. So when you have a cylindrical projection, just think about wrapping a paper in a cylinder around the globe. So with these projections, they preserve distance, but they distort size. And then you have the conic projections, in which you're just think of that paper now in the cone shape that's around the globe. And this projection is good at preserving area, but the area gets more distorted when you get away from those east-west lines that you see in the image, and they're called standard parallels. This can be either 1 or 2 parallels. And then the azimuthal projections, those are really good projections to use, like if you're creating maps of the poles, because it's more or less a flat piece of paper that's touching either the north or south pole. And then even within all of those projections, there's like different types. So another thing that you need to consider is whether a projection is secant or tangent. So a tangent has one line of contact between the Earth and that projected surface. And then the secant projection has 2 or more lines of contact between the Earth and the surface. And if you want more information on the projections, if you go into the RStudio project and go into the spatial presentation notes, there is a link that gives more information about projections. But one thing I just want you to like if there's a take-home message, as you can say, you got from this workshop, is project your data. And you project your data based on, number 1, your purpose, and number 2, where are you like at, where are you creating a map? What are you creating a map of? I'm based here in Missouri. So there's actually a projection that I use that's called Missouri State Plain East. And I use that to create maps anywhere for like the eastern side of the state. There's just so many projections, and yeah, I just highly recommend you read the article on the map projections. Next slide. So in R, what does a projection, like, what does it look like? It's pretty much mentioned as a CRS, coordinates reference system. And as I said before, you need to know if your data set's projected, and then if it isn't, you need to project it. If it is, you need to know your projections, because if you don't, you will make some mistakes, especially if you're doing some spatial analysis in R. If your data is not projected, then you're going to get errors. And here's just an example of some that are in France. Next. And so these coordinate reference systems are also being updated as well, because our Earth is moving as well. So due to the plate tectonics, these systems have to be updated on, you know, on like every so many like years or decades or something like that. But in R2, there's some changes that are going on in terms of how these, how you access these. So in SF version before 0.9, you represented the CRS with the EPSG and the project for string. So the EPSG is like the number of your projection. And then like the prod for string, that's just like a lot of mathematical stuff that I'm not gonna go into. And then if it's SF over 0.9, all you need to do is, you know, you're gonna see the user input, which is the EPSG, and then the WKT that gives you just the metadata about your, I think is a more clean version, to be perfectly honest, about your reference system. Okay, next. So before we start, so now that we've kind of have an idea about what projections are, let's talk about the types of geospatial data that you're dealing with. You either deal with vector data or raster data. Actually, there's more types of data. Like there's 3D data, and then like LiDAR and so on and so forth. But for the sake of this workshop, we're going to just talk about vector and raster. So vector are those top 3 layers that, oh, could you go back? Okay, thank you. Are those top 3 layers. So vector data is either points, lines, or polygons. On the top layer, you have points that represent a particular space on the Earth. So it might be customers. It might be like incidences of, I don't know, like bus stops, things like that. Incidents of like car accidents. And then you have lines, which can represent streets or railroads. And then you have polygons, and polygons can represent parcels or buildings, or even polygons can represent like counties and census tracts. Like I do a lot of work with census tracts. And then the other type of data is raster data, in which it is a grid of cells, and each grid, each number in the grid is representative of a particular type of feature on the Earth. This is like some examples of raster data is like soil analysis data. A lot of soil data is in raster format. So each grid will represent kind of like a soil type, Land area classification is also one. So like if you're an urban planner, you might be dealing with this. You might want to calculate the amount of green space that increased or decreased. And you can do that easily using something called roster math. And all of these layers are essentially a representation of a real world. Not an accurate one, because it's very hard to, you know, actively display the world, but it's as good as, you know, it's a representation. So you have to keep that in mind. Next. So I already explained all of this, but one thing I do want to point out is that the data itself for the vector objects is stored in either a database or in several files. So the vector data I mostly work with is called a shape file, which is actually 5 or 6 files that's within one file. And one file represents the database. Another file will represent that it's projected. Another file will represent like the actual, like, you know, like the line. So it's just so many files that represent one file. And then there's another one called GeoPackage. That's new out on the geospatial front, and that's getting more ground because just it's a little bit more simple. Like with a shape file, some people like to, like if you have window, like if, you know, you might like copy and paste something and forget one file and then you're in big trouble. But I think for the GeoPackage, I think everything's in the package. So next. So let's talk a little bit more about rasters. So the raster is defined by its rows and columns, and then like its extent. So you might just have like, you know, it might be just an extent of a national forest. And then also there's the spatial resolution that you have to think of as well. And this is pretty much how raster data is represented. You'll have like ones that might be like water, zeros are probably no data, 2 might be land. It just really depends on the raster that you are dealing with. Rasters that I usually deal with are just like satellite imagery. Yeah. Next. So there's various packages for reading geographic data in R. In the past, you had SP, Argudal, that's what we call it, at least at work, Argudal, RGeos, and raster. But the packages that a lot of people use nowadays is SF, stars. Personally, I haven't used stars, but I know Jacob or Sebastian has, in Terra. Next. So it's quiz time. So what is the first question you must ask yourself when you have a problem with your spatial data manipulation? You know, did you reboot your computer? What is the projection? What is the format of your data? And who in the world taught me this stuff? Because that's going to be the person we blame when we get it wrong. So you can either answer, you can just answer in the, I wish we could make a little poll, you know, that would be nice, but I don't know if we can. Just, but
I can try.
I can answer audio.
Oh, okay, go ahead, go ahead. Yeah, it seems like we're getting some responses, but what do you think?
I think it's the projection. Alex thinks it's the format.
It is B, it is the projection.
Huh.
When I was taking, like, because of like, I studied geography, I took several GIS classes. And I remember I thought I projected the data and I didn't. And then when I get my lab back, I get everything right, But then I don't. And my TA would always write, you forgot to project your data, minus so many points. It happened like 3 to 4 times, you know, and I was taking, I know I hate to like call myself out or like whatever, but this was like an advanced GIS class and I was still doing that. I was like, I thought I projected the data. And you know, it like, I was using a software program. So actually I did not project the data. I did something called on the fly projection. And yeah, so that's going to be pretty much like, if someone's like, I have a problem with my data, the first thing I'm going to ask is, did you project your data? So
What happens?
Is B.
What happens, Doris, like if you're making a map and you don't project the data before you make the map? Can you even make the map, or does it just like look funky?
You can make the map, because I made the map and it just looked a little funky. And that's when my TA's like, you didn't project your data. I wish I could show like a picture of what I wish I could like show it, but like an unprojected map distorts, like your state will not look like your state if it's unprojected. It will look, you will know something's, it really depends on the state, because some states are like, you know, they're box shape or rectangular shape. But like for the state of Missouri, like there should be a little curve on the top and a little, you know, like a little like inverse, like an inverse curve or whatever you want to call it on the bottom. Like there should be a little curvature. But if you're just seeing like a flat top and a flat bottom, I just know for the state of Missouri, it is not projected. Yeah.
So it's like skewed or
it just doesn't, it just looks a little funky.
Got it. Thanks.
Yeah. And that's more like with experience, because I did notice that people who are new to mapping, they're like, oh, I made a map, it looks great. But then like when you see some people who like they've been making maps for a long time and they're like, that wasn't projected. So yeah, it looks twisted. It just doesn't, it doesn't look right. And you know, when you, and if you're, especially if you're working in a particular area of interest, you're gonna know, you're gonna be like, this is my area, I've been projecting my data, I know what it looks like projected. And if someone on your team gives you something on not projected, you're gonna be like, no. And then that, you know, and you'll know why, because it is a clear, you'll be able to spot it. Okay. So before I ask if there's any questions, I just want to summarize everything. So you have your projections, which is the main problem. And it is different depending on the, I would say, the location and the spatial extent. If you're dealing with like a smaller area, like I'm dealing with St. Louis, I'm going to use my Missouri East State Plane. If I'm dealing with a couple of states, I'm going to probably look for a projection, like depending on like if I'm doing Missouri, Illinois, you know, like some other states in the area, I'm going to choose a projection that might have all of those states within the projection. And another thing that's important to know is that vector data is points, lines, and polygons, and raster data is a grid. And I want to re-emphasize that these are not the only type of spatial data, but I think when you're getting into this, this is the data you're going to be dealing with. So are there any questions? Okay, if not, I'm going to just move on. Next slide. So let's talk about reading and projecting data with SF. Yes, everything is fine with SF. Next. In order to read in your data. So a lot of the data that you're going to see for this presentation actually is like data of France. Sebastian's from France, so he came up with the data for these exercises. So Sebastian had these spatial data of first order administrative districts called departments. So I guess they're on the same level as maybe a state, I guess, if you want to have a US equivalent. So you would read these in with read _ SF. And oh, oops. And yeah, it handles all formats by GDAL. And if you want to know what GDAL is, I would just yeah, just click on the link. So you have a CSV, map info. I don't usually deal with that. Google Earth, GeoJSON, PostGIS. It just handles a lot. The most used is the Esri shapefile. I mentioned this before. It's a minimum of 4 files, sometimes 5. And then they also deal, which I like, is the geopack package. And I'm making myself use this because I just think it's better. And it's starting to become more and more of a standard. I wouldn't say it's like right now the standard, but if you want to continue, if you are like, I'm in this map making thing for it, you know, for like a long time, I will familiarize yourself with a geo package and start using them a little bit more. Next. So here is the, like if you want to know if your data is projected, you can use ST_CRS. And with this, you can see the, like the information about your projection, what I call the metadata about it. And it talks about the datum, the ellipsoid. I'm not gonna go into that. And it just gives you all the information you want. Next. And let's just say that you want to project your layer into a new coordinate reference system. Then you would use ST_transform to do that. So you'll transform that from one CRS to another. Next. And then when it comes to points, you can use the read _CSV with no problem. And it gives you exactly what you need. Like if you can see this, like this output, it has your ID, your longitude, and your latitude. And that is what you need, your longitudes and latitudes, to turn those dots into spatial dots. Because right now they're just dots in the they're just records in a CSV file. Next. So, so you would use ST as SF to transform it into a spatial data set. So with these cafes and bars CSV, they are now being turned into a spatial data set with WGS 84, which is like, it's not really, it's not really a projection, it's not, but it's like, it gives you like, it puts those latitudes and longitudes on the map for you. But I will tell you, if you ever take a class in like R spatial or whatever, and you submit a map with the 4326, you'll probably get some points taken off because it's not really a projection, but it gets your points into the program. And then after you do that, you need to change your projection to the appropriate projection. So something appropriate for France. And one thing that I would want to stress, because I've done this myself and it's caused me a lot of strife, make sure you put the longitude first when you're doing the coordinates, then the latitude. I'm always like latitude, longitude, but no. In this case, longitude, latitude, because your points will just be flip-flop and you'll be like, what in the world did I do? I don't get what I'm doing. And you'll do it for 30 minutes and then realize you need to just flip it. So Next. So after you create like a spatial object in R, you can export it. Let's just say like, you know, you're working in a group, everyone's have their own different workflow. Maybe you're an R shop and you want to send your newly creative spatial files to a group that primarily uses QGIS or, you know, QGIS or an Esri product or Python or whatever. Well, you can export this into a geo package or a shapefile or a GeoJSON if you're dealing with JavaScript and so on and so forth. You use write_SF to do that. And you do that, you know, you have your stuff in a folder, you can zip it if you want, and then, you know, send it to your coworker. But make sure that you write your file out, because it will not work for others if you don't. Next. So now, a little quiz, because we're at the end of this section. So what is, this might be a little tricky, maybe not, maybe. What's the correct way to deal with this text file that needs to be used as a spatial points data set? So you have these points, like I said, 4326 is the WGS84, and I said my words about that. So you can put it in the chat. You can, you know, just go ahead and answer if you want. I'll give people a little bit of time to figure out what's going on with this. So are there any takers in the chat window? This was a little tricky one. It said A, but technically with the ST transform after. Two, 2, 1, 5, 4. I want to say these are points. Okay, I'll just give it a little bit more. Okay, I will reveal. I know everyone's like, I want to know the answer. It is A. But I do want to address what was mentioned in the chat about yes, like after, like you are correct. You first like bring it in with the WGS84, so it's in that map, that's, you know, that 2D spatial plane with WGS84, and then after that, yes, you would do an ST transform to 4326. And you can do that because you already have it in this like projection that's not a projection. And yeah, so that is correct. But the first step would just be putting that in using WGS84. So yeah. Next slide. Okay, so I talked about SF and I talked about read and write SF, and then how to get that data into that R workspace. Next. So if everyone has their R Studio Cloud project open, you should see some exercises. And if you could start with the exercise, spatial data, vectors data, read and project. Please do not knit the whole exercise file. You will get errors. Just fill in the blanks and then run the code chunks. I'll time 15 minutes. And please stop once you reach drawing maps with R, but there'll be someone in each room to help you. So if we could break out, there are 14 people here. Sections. Oh, okay, I guess I'll say it again. I am going to now, I realize we're a little bit, like a few minutes before 7 and have 2 more sections. So I'm going to try to get through these parts as quick as I can so you can do the exercises. Okay, next. So the packages that we're going to really talk about today is tmap. And there are many packages to create maps, but some of them are not directly dedicated for making maps, like ggplot2 or rbase. But some like leaflet and mapdep and mapview, they are. The nice thing about tmap is that you can tap into leaflet, which you will be able to experience in the exercise. Next. So before you make a map, you really need to ask yourself, do you really need to draw a map? If there is a meaningful spatial distribution, then yes, you should make a map. If not, then you should maybe use another data visualization, like a bar chart. On these 2 images, they're showing the same thing, but maybe the person created the map because they want to show more like more of the like geographic distribution of these cafes. So if there's a spatial issue, then you should make a map. If not, then maybe something else would be good. So just to reiterate that point. Next. And then there's even, like, this is really touching the tip of the iceberg, maybe the tip of the iceberg. But there's different symbologies that you will be using when creating your maps. You don't want to make a map and not think about this. It will be very hard for people to see your message. So you would map qualitative data different than quantitative data. And then you would have to even ask yourself some questions if you are dealing with quantitative data, how to express these spatial relationships through color or size. Next. If you want to read some spatial data, you can use read_SF to do that. And yeah, that's pretty much that. Next. And then some other things you need to think about after you read that data set in with tmap. What are you mapping? Are you mapping points, lines, polygons? And you might be asking, why text? Well, there's, when you're mapping things, there is an option to have annotations in which you can have, like, if it's like the text of cafes and restaurants in a particular department in France, and you're focusing on one, you can have the labels pop up on top of the names of the restaurants. I think that might be more for people who are maybe use like they export their map out to like Illustrator or something like that and want to do more editing. So that's a matter of personal preference. Next. Could you please go back one? So this is first of all, I want to caveat, this is for demonstration purposes only. You would totally not make a map this way. There's way too much going on with the legends and the colors have no purpose. But this is to show that you can map stuff and you can have a legend. This is the structure of how you would map your make this map. So first you need to, so for this map, first the shape, Europe, TM shape Europe. Then after that, that's that whole base map of that part of Europe. Then after that, you're bringing in the polygons. So TM underscore polygons. Plus, you want to create your shape using that department shape file that you have. And then you want to fill it with a particular color. So that's what this code is doing here. Next. And if you want to darken the borders, you can do that as well. You keep on layering on to create your map, adding TM this, TM that. Next. So now I'm going to talk about the how to make maps, thematic maps with tmap. So every map that you make, if you're going to send a map out to someone, if you're going to have a map in a presentation, you need a scale bar, a north arrow to show the direction of, like, it gives you an orientation, and you need the title. You also need a data source, a text, like some text that says where you got your data from. But if you look at this code, you add things with just doing TM borders plus TM scale bar plus TM compass, and then you set the parameters for where you want it. Then TM layout, which is where you can put the title. So it's just layering upon layering upon layering with the code. Next. So what is the correct code to draw that map? The departments 193 map. And the departments 193 is a spatial object of polygons. So you can put the answer in the chat, or just say the answer, whatever works for you. That's funny, Ola. That's funny. Okay, so the answer is actually B. I mean C. I'm so sorry. C. Sorry, it is C. Why is it C? Because it has that layering. You define your shape, then you define, which is that spatial object, which you say it's a polygon, and TM layout is where you put the title. D, labs, that is a ggplot2 function. So that would not be used for tmap. Next slide. And the summary is, if you don't need a map, don't make a map. Choose, like, know what data you're working with, points, lines, and polygons. And when you create that, after you create your layer with TM shape, then use the appropriate function for that. And then if you're ready to, like, send something out to the world, make sure to add the scale bar, the compass, so that north arrow, and then a title. Next. Now we're going to have, actually there's going to be 20 minutes for this, because I want everyone to have a break. So if we can get back into those breakout rooms. And make sure you start with drawing maps with R and then stop when you get to manipulating vector data with dplyr.
Okay, I'm going to open the breakout rooms now. We're just gonna wait for one group to come back.
Yeah.
Yeah. But I hope you guys got a chance to have a break and get to know each other a little bit more during our last breakout session.
Yeah, I just need the slides to come back.
Okay.
I'm on it. Sorry.
No problem. Yeah, I'm going to try to go through this section quickly because yeah, I'm kind of running low on time, and also for the next exercise, it'll only be 10 minutes. Okay, so the cool thing about tmap is that you can manipulate vector data with dplyr. Next slide. So with SF, your data is in, it's in a database, it's rectangular. So whether it's a CSV or a shapefile, you're going to have an underlying database. Next. So the really, really cool thing about tmap is that you can that you can run dplyr, SF, The cool thing about SF is that you can run dplyr on the object. So you can do the same type of, use the same type of dplyr verbs and apply it to these spatial frames. So this is the Breton region of France, made up of 4 departments. And so these were singled out actually through a select and filtering operation. Next. And a lot of, sometimes when you're working with spatial data, one of the things you might have to do a lot of is dissolving. And so you can actually do a group by and summarize to dissolve those departments into regions. Next. And I could really get into the weeds with this, but for the sake of time, I am not. You can do joins with data sets as well. When I'm working with spatial data and doing this kind of operation, usually what I'm doing is I have a census shapefile of some census tracts, and let's just say I want to add the population, I want to attribute the population to each tract. I would do that by doing a left join, in which I am joining the population data to the census tract based on a common column in both data sets, which is called a key. So for me, I am a left join person, but it really depends on what you want to do with the data. But I'm not going to get into the weeds with the joins, just due to time. Next. Yeah, so you can, like my census example, this one is going to join the number of inhabitants by age CSV to the shapefile of the departments. Next. And this is just showing you that you have that common key. Now that common key might not be the same column name in the different data sets. So in this inner join that's happening, it's only doing it, it's doing it by code department in one and then ID department in the other, but it's the same information. So sometimes that happens and you need to double check your fields before doing a join, or else it's going to be a hot mess. Next. Okay, I know I went through that really fast. I'm gonna I'm gonna give the answer to this due to time. So the answer is D. You run an inner join on two data sets where you want to only keep spatial entities that there is a match. An anti-join does like the opposite of that. So you would do an inner join by doing getting that restaurant CSV and joining it to the France L93 shapefile. So yes, next. So I went quickly over how you can use dplyr on SF objects. And if you want to do some dissolving of your smaller administrative units into bigger ones, you can use group by plus summarize. And there's also compatibility with tidier functions. So I apologize that I went so quickly, but I want you to have time to do the exercise and a little time for Q&A after. Next. So it will not be 10 minutes. It will be, 15 minutes. It will be 10 minutes. So this is the final exercise. And yeah, good luck with it. I hope you're enjoying the exercises so far. Okay. Welcome back, everyone. So now we are at the end of our journey with tmap and SF. So where do you go from here? Next slide. Yes, there is a lot more. As I previously said, we only touched the tip of the iceberg. Next. We have a little time left, so I will go briefly over these functions. So we already went over STCRS, but when dealing with your data, sometimes you need to actually set the spatial extent of your data. And this becomes more of an issue when you're doing spatial analysis, because if your extent's too big, it's going to have an effect on your study, especially when it comes with geostatistical methods. So you can set the spatial extent to like manually, or you can set it to an area of interest, like maybe another SF file or something like that. And then ST join does a spatial left join. So a spatial join, if you remember the map with the departments and the cafes, what that essentially would do would join that points file to the actual shapefile of those departments. So if you wanted to know how many cafes were in each department, you can do that left join, and then you can see like, it'll say like how many points is in each of the area. So the join is based on the location, the boundaries, not the key. So for intersection, it's things that are the same between two of the files, between two data sets, shape files. So you might, this might be something like you're looking for a suitability analysis on like the best spot to make a new coffee shop. Usually you have all these criteria and you're doing all these searches and selections and so on and so on and so forth. And you might be doing some intersections so you can find areas that meet all that criteria. And then when you crop something, you're just cropping it out. Let's see, what else? So one thing that's really important, since I am talking about suitability analysis, is finding the buffer area. Like, for example, like for the coffee shop example, it might be like, oh, it needs to be within 10 minutes of a major metro line, where you can do a buffer of areas. And it might be by the centroid, which is like the center, quote unquote, the center of the polygon. And then you can do a buffer around that. Or you can do like a buffer of schools that are within 10 miles of a bus stop. So for me, the ones that I usually use the most out of this is set STCRS and STJoin and STcentroid. But again, that's really based on the work that I'm doing. So know that everyone works in spatial data in different ways. And they're going to have their own set of functions that they use. And I put in a book that Robin Jakov, and then Robin Lovelace and Giannis Mukunchal made, called Geocomputation with R. I highly recommend that if you're really interested in learning more how to do spatial manipulation to R, to read this book. I found it a very good foundational text for someone who wants to exclusively work within the R ecosystem in doing spatial calculations and spatial functions. So please give it a read. So if you want to know more about those functions, actually we did cover those in the original user 2020 workshop, and all of those workshop materials are actually online in the GitHub repo. So next, and I'm done. So if anyone has any questions, whether over the exercises or just in general dealing with R spatial, I will try my best to answer those questions. You can put the questions in the chat, or, you can ask.
Silent, I saw some silent claps. Thanks for your.
Oh, will you give the answers to the exercises? Actually, if you look into your the RStudio cloud, the solutions are actually there. I didn't want to really point that out because you might get frustrated and be like, I'm just gonna look at the answers. But that's why we had the breakout groups, so everyone can work together to figure out the answers. But yes, the solutions are in the RStudio cloud projects.
I have a question.
Mm-hmm.
Is there a good, I know you mentioned, I think, one website earlier in the slides, but is there a good sort of repository for maps of, or these sort of geo packages or SH files of different regions, and stuff like that you can just like browse through and work from and add your own data on top of?
It really depends on where you're working, because that's actually my job, is that people, let's say some people are trying to find some data. Like I have a lot of students having to work, they're doing spatial stuff in St. Louis, and they're looking for schools, or they're looking for like walk score data or something like that. That's more of a matter of like if you work in an academic institution, then you should definitely connect to, if you have a data services division in your university, or a GIS librarian, because they can help you with that. Outside of that, it really depends on what you want. Do you want government? Are you looking for government data? Are, you know, in terms of like census data? Are you looking for environmental data? I can name one package that comes to mind that I really like with census, and it's Tidy Census. That's a really good package. And it, like when you're working with census data off of the census website, some things can be a little bit of a headache when it comes to joining the data, because the census data has some extra zeros in their common key known as the geo ID, and you have to get rid of those. And then after that, join it to the shapefile. But this Tidy Census one has all that in the package. One of my friends, Shell Kariuki, she made a package for the Kenya census. So it really depends in terms of RM packages, who's making what. And someone might tweet about it or something like that. But I can't say, oh yeah, there's this site and it has all the data sources, because I mean, people are making packages all the time. So it's hard to keep up in terms of that. And it also depends on what region you're in too.
What about just like the basic maps? Like if I just wanted like Texas and then like the counties, the borders of like the counties.
That would be, you can use Tidy Census, and you can also use that, use the US Census Bureau. Let me put that in. They have, every year they work on this data set called Tiger Lines. And let me put it in here. And so the first thing, if you're dealing with census data, you need to get the shape files. That's personally why I like Tidy Census, because you don't have to do all that. And then you need to go to data.census.gov, look at what you're looking for, download the CSV if you're looking for some kind of demographic data, and then joining it together. If you only want the shape files, then the census website is that is the best source for any US based boundaries. And every year they update it, so it's well maintained and well documented.
Awesome, thanks so much.
Are there any other questions?
I have a quick question. What is a datum, and can you have the same projection for the same CRS with multiple datums?
A datum is like a mathematical model that's based on a particular like spheroid, because the measurements are like based on different parts of the world. Like for example, you wouldn't use like a datum in which the basis, they started the measurements like in Japan and Kansas. I say Kansas because one of the, I think it's a North American datum, that's where they started that's the point where they created that mathematical model. So the farther out, so you have to think about the datum too. But it is based on the spheroid, and that's always being updated too, because due to all, plate tectonics, the gravitational pull, the spheroid does not stay the same at all. It's like this funky, wonky, it's not a complete circle. And there has been incidents in which I remember I was told, know your datum, because you use the wrong datum, you can really mess things up. If you're making like transport maps, like navigation maps, which uses a particular projection, which is also controversial. One popular projection to use is Mercator projection for transportation. It preserves distance, but it distorts the area, which is why it's very controversial, because it shows Africa being smaller than countries it's actually bigger than. But it's great for navigation.
Yeah.
But if you use the wrong datum and you're making navigation charts, you can cause major trouble. I wish, let's see if I can find it. Let's see. I feel like I have to figure it out. But yeah, there's been incidents in which they used the wrong datum and there was an accident.
Oh, geez.
That's what I'm trying to figure out.
So that, if I may kind of lead into the next question, then the one thing that I always struggle with is I'm a biologist. I don't do, I make maps for prettiness, you know, but I want to make sure they look right. So I try to find the right projection to use. And often I just, you know, kind of Google around until I find what do people typically use when looking at this area. But it's really hard sometimes. Like maybe I just don't know where to look. Is there like a place where you can look to find out what CRS you should be using?
Yes, there actually is. Let me find that website too.
Oh my goodness, that's amazing.
Yeah, there is. I need to it's I think it's this one. I think it's this one. I don't know. There is a site that I use. EPSG.org has it where you can look it up. I believe this site has it. Yeah, if you click on the map search, you can choose by location what EPSG that you're working with, you want to work with. Yeah, that's one way to do it. What's another way? So are you working mostly in the US or outside?
Canada.
Oh, Canada. Yeah, EPSG would be the best one.
Yeah, that's cool. I've never seen the map search before.
Yeah, that's new. That's definitely new because I remember they did not have that. So I don't know. I'm just gonna put something really arbitrary, like put like Vancouver and see what it says. Oh, it won't let me.
It looks like it also has a way of like essentially specifying like a polygon, and presumably that will give you also like taking into account the extent. Also, sorry, I feel like I'm monopolizing, but I have one more question. Is it, if you really have a small limited area, it's okay to just not project your data, right? If you're looking at like a field site in a provincial park kind of thing.
Are you gonna make a map of it? Are you gonna, if you're gonna make a map of it, if you're going to run spatial calculations on it, let me tell you when I don't project data. When I want to see if a file actually opens, that's when I don't project my data, because I just need to see if the file's open. Or I want to look at the data. I want to look at, well, I want to see what's in the data frame. I won't project the data. It is mainly just a informational, personal informational, like dig for me. You should if you are creating products for people or an analysis for people, it does not matter how small the area is, because when I was a TA, students were maybe just working, like I had a friend who, she did this community garden area. She did drone, yeah, she made drone, like made imagery from drones, like from just doing a drone of the school community garden, like every so many days. When she put that data in, she projected it, even though it was a very small space. It's, yeah, you have to.
Okay, good to
Unless,
know.
yeah, I mean, it is, yeah, there's not one thing you don't get from this workshop. It is, please project your data, because you think it won't catch up with you. It'll catch up with you sometimes. Like I've seen people, like I've seen map contests and I'm like, ooh, you didn't project your data. Or I've seen like studies, oh, here's the schools in this region. Ooh, you didn't project your data. And like one of my friends actually like pointed it out. Wow, this person didn't project their data. And I was like, oh, yeah, they didn't.
Okay, good. I know. I will project. Thank you.
Yeah. Yeah, it just looks like if you yeah, it just looks bad. Like the bigger the area, the more distortion you can see. The smaller the area, you think you can get away with it, but someone has a trained eye and they're like, you didn't project it. AKA the first 4 lab assignments I had like in the GIS class. So that was the constant feedback I got. And I'm like, how did she know? It was just like a small area. It wasn't even that big of an area, but she knew it wasn't projected. And I just got points deducted every single time.
That's crazy. I didn't realize it was that, like that you could tell. So that's really good to know. Thank you.
So, well, I am done. And if you have any questions, feel free to I'm sorry, I'm like losing, I don't know what's going on here. But yeah, feel free to add me on Twitter. I've been a little MIA on Twitter. So I'll put my Gmail in the chat, and you can send me an email if you have any issues or questions or anything like that. That's probably the best way to reach me right now, because I'm a little busy right now, so I haven't really spent time on Twitter nowadays. Thank you, Melissa. And I hope you continue to learn more about spatial data, because spatial data is special data. That's what we say at work. So even when you do spatial statistics,